Artificial intelligence is often discussed as if it were a single unified technology. In reality, AI includes systems with very different capabilities. This video introduces how AI is classified based on what systems can actually do, rather than how they look or how impressive they appear in demonstrations. Classification matters because it shapes expectations. When different kinds of AI are grouped together, people may overestimate or underestimate capabilities. Clear categories help policymakers, organizations, and the public reason accurately about limitations, risks, and appropriate uses of AI systems. Popular discussions often blend scientific terms with fictional ideas. Media language prioritizes drama and accessibility, while technical language emphasizes precision. Understanding the difference helps prevent confusion between real technologies and imagined ones, especially in public debate. One common and useful way to classify AI is by capability. This approach focuses on the range of tasks a system can perform and whether it can generalize knowledge across domains, rather than on form, interface, or popularity. Using capability-based classification, AI is commonly divided into three categories: narrow artificial intelligence, general artificial intelligence, and superintelligence. Each category represents a fundamentally different level of scope and flexibility. Narrow AI refers to systems designed to perform a specific task or a narrow set of tasks. These systems are optimized for particular problems and operate within clearly defined boundaries set by their training and design. Formally, narrow AI applies intelligence to a single domain. It cannot transfer what it learns to unrelated tasks. Success in one area does not imply competence in another, even if tasks appear superficially similar. Narrow AI systems often perform extremely well within their domain. However, they lack flexibility. When conditions change or inputs fall outside expectations, performance can degrade rapidly. Learning in narrow AI is constrained by task definitions and available data. Improvements occur through additional training or tuning, but only within the original problem space the system was designed to address. Examples of narrow AI include search engines, image recognition systems, and language translation tools. Each performs a focused function efficiently, without understanding broader context or meaning beyond the task. Many everyday systems rely on narrow AI, including recommendation engines, spam filters, and fraud detection tools. These systems quietly support daily activities without requiring direct user awareness. The strength of narrow AI lies in speed, scalability, and consistency. These systems can process large volumes of data rapidly and apply the same logic reliably, outperforming humans in repetitive analytical tasks. However, narrow AI cannot reason broadly or understand context beyond its training. It does not possess common sense or general understanding, even when outputs appear fluent or intelligent. Because narrow AI can produce impressive results, it is sometimes mistaken for general intelligence. This appearance can be misleading and contributes to inflated expectations about what current systems can do. Narrow AI dominates today because it is feasible, controllable, and economically useful. Its limitations make it safer to deploy than broader forms of intelligence that remain theoretical. General artificial intelligence, or AGI, refers to a hypothetical system capable of performing any intellectual task that a human can perform. Unlike narrow AI, AGI would not be limited to one domain. AGI is defined by flexibility rather than specialization. It would learn across domains and apply knowledge in unfamiliar situations, adapting without being redesigned for each new task. Key properties of AGI include transfer learning, general reasoning, and adaptability. These abilities allow humans to solve diverse problems using shared cognitive structures. An AGI system would exhibit capabilities associated with human intelligence, such as understanding context, planning actions, and learning efficiently from limited experience, rather than massive data sets. If achieved, AGI could address a wide range of problems without task-specific engineering. This potential explains why AGI attracts significant attention despite remaining unrealized. Currently, No system qualifies as general artificial intelligence. Existing AI systems, including advanced models, remain narrow in scope despite impressive performance. AGI is difficult because intelligence involves more than pattern recognition. It includes common sense reasoning, contextual awareness, and embodied experience that current systems lack. Important components such as understanding cause and effect, forming mental models, and grounding knowledge in physical experience remain unsolved challenges in AI research. Structurally, AGI would require flexible cognitive architectures rather than task-specific pipelines. This represents a fundamentally different design challenge from narrow AI systems. Many products are incorrectly described as AGI for marketing purposes. These claims usually reflect misunderstanding rather than genuine technical capability. Superintelligence refers to intelligence that exceeds human capability across most domains. This concept extends beyond AGI into territory that remains entirely hypothetical. Artificial superintelligence would outperform humans in reasoning, creativity, problem-solving, and strategic planning, not just in isolated tasks. Theoretical discussions include forms such as speed-based superintelligence or systems capable of strategic reasoning beyond human limits. These ideas remain speculative. No empirical evidence supports the existence of superintelligent systems, and no known pathway guarantees their development. Superintelligence is common in fiction, where it is often portrayed as autonomous, conscious, or threatening. These narratives shape public perception more than technical reality. In reality, no superintelligent systems exist today. The concept is discussed to explore long-term possibilities, not current technological conditions. Concerns attributed to AI are often actually concerns about hypothetical superintelligence rather than real, deployed systems operating today. Separating evidence-based risks from speculative scenarios helps maintain rational discussion and prevents misplaced fear or distraction from real issues. A critical distinction exists between real AI systems and hypothetical ones. Conflating them undermines effective governance and public understanding. Real AI systems are narrow, task-specific, and deployed under human control. These systems are the ones shaping society today. They rely on data, predefined objectives, and human oversight. Their behavior reflects design choices and constraints rather than autonomous intent. Hypothetical systems such as AGI and ASI remain research concepts. They do not currently operate in the world and should not dominate policy decisions. This distinction matters for regulation, governance, and responsible deployment. Policies should address real systems with measurable impact. Confusion often arises when all AI is discussed using the same language. Precision improves accountability and decision-making. Scientific caution emphasizes clear definitions and evidence-based claims, helping prevent unrealistic expectations and misplaced trust. Evaluating AI claims requires focusing on demonstrated capability, not labels or promotional language. Avoiding category errors helps societies focus on managing existing systems rather than hypothetical extremes. Responsible communication about AI relies on accurate classification and careful distinction between current reality and future possibility. Decision-makers benefit from understanding which type of AI they are dealing with before adopting, regulating, or deploying systems. Society benefits when attention is focused on managing real systems responsibly, including their limitations and impacts. The central takeaway is that nearly all AI in use today is narrow AI despite frequent claims to the contrary. Clear classification enables better governance, safer deployment, and more informed public discourse. Understanding types of AI helps balance innovation with realism, preventing both hype and undue fear. When we classify AI accurately, we make better decisions about where it can help and where caution is required. Next, we will examine common myths about artificial intelligence and contrast them with technical reality to further clarify what AI is and is not.